Our next test will be over types of chemical reactions. Just to review, we have several evidences that we all need to see one of these, that a chemical reaction occurred. A chemical reaction must have occurred if there is formation of a new solid, liquid, or gas, and if without us trying to cause this to happen, there was either a release or a consumption of heat, light, or electricity. There are several main reaction types, and some of them overlap. Synthesis reactions, which we can also call combination reactions, decomposition reactions, double displacement or double replacement, and oxidation reduction. First of all, synthesis or combination reactions involve multiple simple substances reacting to form fewer, more complex substances. A synthesis, here are a few examples. We have over here hydrogen gas with oxygen gas to make water. You can see more particles and they are simpler, making fewer and more complex molecules. Here, you know this reaction is, that equation is the equation for photosynthesis from your biology class. You can see we have 12 smaller molecules making 7 other molecules, one of which is more complex. And here we have 2 simpler molecules making 1 molecule. This would be how some acid rain is formed by sulfur dioxide gas reacting with the water in the air. Decomposition is the opposite of synthesis. It of course means breaking down. So you start with more complex things and end up with more and simpler compounds or substances. So ammonium carbonate making ammonia, carbon dioxide, and water. Calcium carbonate, which can be heated until it decomposes into calcium oxide, which is called activated lime industrially, and carbon dioxide gas. Or if you had molten, look, this is liquid sodium chloride, you could run electricity through it and have the sodium migrate to one end and form pure sodium metal, and on the other end you'd be making this toxic gas, chlorine gas. Double replacement, we've already talked about. These can be precipitation reactions or acid reactions. First, we'll talk about precipitation reactions. We have to see will the reaction happen or not. In order to figure that out, we have to check solubilities. So we check solubilities using our star reference chart materials. We've got solubility tables right here. Notice that all the things that we can check are anions. They're all negatively charged. So we look at the compounds that we say should form by doing the double replacement, and then we see whether they're soluble or not. If they're in the insolubles but involve an exception, then they'll still be soluble. If they're in the soluble section but involve an exception, then they will be insoluble even though they were normally soluble. Here's some examples. You can see we just took the carbonate and put it with the barium to get barium carbonate. You look up carbonate and you'll find that it's the barium is not an exception for this insoluble carbonate. Nitrates are always soluble. Alkali metals are all soluble. That's why that's aqueous. Here we have lead 2 acetate. That's a soluble substance, but lead, when it gets together with chloride, makes an insoluble substance according to solubility rules. Same thing with zinc hydroxide. So we're just using solubility rules to predict whether a reaction happens or not. If there had not been any solids formed, we would say there would be no reaction. Here we have acid-base reactions, another form of double replacement. And acids, you'll remember, donate H's, and bases, the way we're presenting them today, donate hydroxides. When you put an H with an OH, you make a water. Or in this case, 2 H's with 2 OH's makes 2 waters. And what's left over, the metal and the non-metal, make an ionic compound of salt. Here is hydrochloric acid with the H getting together with the OH to make H2O, and the potassium getting together with the chloride to make potassium chloride. And notice what drives these reactions to happen is the fact that we've formed a new liquid, water. We have some exceptions about just things to watch out for. 2 main compounds to watch out for. So here we've formed, we predict that we would form sodium nitrate and carbonic acid, and they both, according to solubility rules, should be aqueous, so we might have thought there would be no reaction. But carbonic acid decomposes into water and carbon dioxide, and that's why actually we can replace the carbonic acid with the water and carbon dioxide, as I've done here, and you can see actually we've formed a new liquid, a new gas, and so that's evidence that this should be a chemical reaction that does occur. Another exception involves ammonium hydroxide. Here we can see we formed ammonium hydroxide, but ammonium hydroxide decomposes into water, a new liquid, and ammonia gas, a new gas. And so when you substitute the water and ammonia that for the ammonium hydroxide that it's decomposed into, the ammonium hydroxide is decomposed into these two things, then you'll see, yes, we have evidence, or we predict that there should be such a chemical reaction to happen. But you got to watch out when you see either NH4OH, ammonium hydroxide, or when you see carbonic acid, you should realize the reaction actually does occur even though you would predict them to be aqueous. Okay, oxidation reduction. This is another type of reaction. The reduction, here's my simple way to remember it. Reduction means charge goes down. Reduction means charge goes down. Then the opposite of reduction is oxidation. Oxidation means charge goes up. So let's an example. Here we have magnesium. It's in its pure elemental form. Note this, note, any element in its pure form has a charge of 0. So this magnesium has a charge of 0. Magnesium is supposed to be reacting with oxygen here. This is O2 gas. That's the pure elemental form of oxygen, and it also then has a charge of 0. Now over here, the oxygen is oxide. It's got a -2 after reaction, and the magnesium after reaction is a +2 ion, and so both of these have changed charge. Somebody's charge went down, somebody's charge went up. There always has to be true all the time. If there's a reduction, there has to be an oxidation. So our reduction was oxygen going from 0 down to -2, and our oxidation was magnesium going up from 0 to +2. Oxidation reduction reactions can come in a couple of different ways. One of them is single replacement reactions, the other is combustion reactions. There are other examples too, like the one we just did was actually a synthesis reaction. But we'll go over single replacement reactions. For single replacement reactions, we have to predict whether the reaction should actually happen. And so we're going to look at this activity series that's provided for us on a star chart on the same panel as has our solubility rules. And we're focusing on the metals here in the activity series. And so the idea, but also, for the idea is that for the replacement to happen, the element in the reaction must be higher on the activity series than the ion. That's our rule, and it'll make sense as soon as we show you an example. So here we go. Here we have a metal, and this is elemental, right? It's the pure solid version of just magnesium. It hasn't reacted. It's an element, so it's got a charge of 0. And here we have iron 3 oxide, because each of these irons has a +3 charge and the oxides are -2s. And we're saying, oh, well, the magnesium looks like it replaces the iron. It's now paired up with the oxygen, and the iron is left alone, pure and elemental. So we have to see, well, should this reaction happen? And so we go over here and we say our rule was the element, that's the thing alone as a reactant, has to be higher on the series than the ion, because this is Fe3+, right? So our element has to be higher than our ion, which is iron 3+ here. And indeed, magnesium is higher than ion. So this reaction, this top reaction, should occur. But our bottom reaction, let's consider that. Our pure element this time is sodium. And we have a compound with an ion of potassium and then sulfide. And we're predicting that potassium would be produced in the pure elemental form and that sodium would be turned into its ion form. But we have to go check our series to see if that works right, our activity series. And so we said the element has to be higher than the ion. And so the element is sodium, but the ion is potassium. So the sodium is not above potassium. So we say this should not occur. There's no reaction. I know we could write the balanced equation, but the reaction doesn't actually happen. This is another oxidation reduction reaction, but look what's going on here. Here we have a non-metal. It's not going to replace a metal, it's going to replace another non-metal, right? So if this could happen, the chlorine would replace the iodine. So the iodide there. So we don't have non-metals on our activity series. What we do have instead is this section of the periodic table, which is the non-metals, right? And we use it just like we would use our activity series. The higher the element is up, on this activity series, if the element is higher, it replaces the ion. So our element here is chlorine, but our ion is iodide. So chlorine is above iodide. So this reaction, this top reaction, should happen. However, in the bottom case, we have calcium chloride, and we wrote it as if bromine would replace chloride in the calcium chloride. But you can see that chlorine is above bromine, and bromine is the element, and it needs to be above the ion in order to replace it, but it's not. It's below the ion, so it does not replace it. So that's how you run single replacement reactions. And by the way, they're all of them are oxidation reduction reactions. You can see here the iodide started out -1, ended up 0. The chloride started out 0, ended up -1. So there was an oxidation and a reduction. But this bottom reaction doesn't even happen. Combustion reactions involve burning in the presence of oxygen, O2 gas, and they usually produce CO2 and or H2O. So here's an example. This is propane, and if it reacts with oxygen, it should produce carbon dioxide and water. So that's a review, or an introduction, and a tad of review over the various different types of reactions. You should be able to do most of your schoolages with this information.